Hey there, folks. Back here. Still looking at application of derivatives, still looking at functional analysis, where we are going to go a little further into all of that and really, I might say, even begin wrapping this topic up, where we're going to talk extreme values now. We're going to look at, in this video, the case for absolute extreme values. And in my next video, look at the case for local extreme values, folks. And that will kind of take us to the end of this discussion on functional analysis. All right. But we're almost there. We got two more videos to talk about where we're looking at the extreme values of a function. And then what we're going to see is a little application of those ideas. How can we use then functional analysis to help us out in the real world? We'll get into a little bit of that in coming videos. All right. But let me go ahead and bring my notes over here. Like I said, we're going to start talking about absolute extreme values. And what absolute extreme values describe are the largest and smallest values that we find in our range. The range of a function is all dependent values that we obtain from the independent values of a function. The largest of those dependent values is the absolute maximum value of the function. The smallest of those values is your absolute minimum value. To go a little further, though, they don't always exist. There are times where the extremes of our functions continue to head off to plus or minus infinity. When we talk absolute extreme values, we are talking finite values, finite boundary values found in our range. The infinite boundaries that might describe a range at times do not describe absolute extreme values. In those cases, we may or may not have maximums or minimums, with depending on whether or not we have negative infinity as a lower bound, we would not have an absolute minimum, or positive infinity as an upper bound, we wouldn't have an absolute maximum value in those cases. Otherwise, yeah, if a range value is finite, if the boundary on a range is finite, it is an absolute extreme value, maximum or minimum, depending on which boundary it describes. For example, we might consider the range of the function f of x equals 5 minus x squared. All right. It has a range. This is a parabolic function. It is a parabola that opens down and shifted up 5 units on the y-axis, which gives it a range from negative infinity up to the value of 5. So it does not have an absolute minimum value, since the smallest range value is never actually obtained. The range values are constantly heading down towards negative infinity. But it does have an absolute maximum value. If we did a further analysis, we would be able to determine the absolute maximum would occur at 0, which would give us an output of 5. 5 being the largest possible range value, the upper boundary found in our range. That value of 5 there is the absolute maximum. All right. Absolute extreme values will describe the finite boundaries found in our range specifically. By definition, we say that the absolute extremes of f occur at x equal to c, where f of c is the smallest or largest value of f found in the range of the function. The value y equal to f of c is the maximum value of f on some interval, if f of c is greater than f of x for all x in this interval. And similarly, the value y equal f of c is the minimum value of f on some interval, if f of c is the smallest value for all x in this interval. That's what the statement is saying here, folks. At y equal to f of c, you will have a maximum value if the output of the function at c is bigger than, greater than, f at x for all other x in this interval. And likewise, f of c is an absolute minimum value of f if f of c is less than f of x for all x in this interval. Right? And I don't know why I'm just saying maximum or minimum here. I probably should say absolute along with that. Absolute maximum value and absolute minimum value. All right? That's how we formally define our absolute extreme values. As for determining them on their domain, over their entire domain, it really just requires a range analysis. You do have to analyze the function's range. You have to basically begin sketching out the function and determine what is the range of our function. That is going to tell you the absolute extreme values for any function over its entire domain. However, if a function exists on a closed interval, meaning that it exists on an interval that starts at a finite value of a and ends at a finite value of b, and we see that here, right? Let f of x be defined on a closed interval of x defined by this interval from a to b. Right? The extreme value theorem, there's going to be a follow-up theorem here that actually guarantees that we will have both an absolute maximum and an absolute minimum value on that closed interval. From A to B, we will have an absolute extreme value, right? If, and I should be careful here, this is if it's continuous. Maybe I should say here is defined and continuous over this closed interval of x. It does have to also be continuous for this to happen. Here's the extreme value theorem. And notice it does say continuous in the theorem. It says if y equals f of x is continuous over x in the interval from a to b, then there will exist both an absolute maximum and an absolute minimum value on this interval. Where these extreme values will occur will be at the critical points in this interval or at the endpoints of this interval. And I have some illustrations for that down below here. The following illustrate a few of these cases where we might encounter maximums and minimum values here. These all illustrate the exact same function on a closed interval, meaning that it only exists from a to b for values of x, and all of these exist from some value of a on the left to some definitive value of b on the right. Each and every one of them, even though they may have different a's and b's, they all exist over a closed interval from a to b. And what you see is, depending on where those endpoints are located, relative to the critical point seen in the graph of the function, right? Well, first of all, what we will notice is we'll always have a maximum or minimum, right? First thing we should notice is we always, in each of these situations here, will always have a maximum or minimum value for our function on this closed interval. And depending on where those endpoints are located, the maximum and minimum values could potentially be those endpoints, as we see in this first graph for both of them, or for the minimum value on the left here in the second graph, or where we're going to see maximum and minimum values are going to be at the critical points. The maximum here at the critical point in this first graph, and the absolute max and mins at these two critical points here in the second. All right. If our function exists and is continuous, starting at some value of x equal to a, all the way out to some value of x equal to b, it will always fall between a maximum and a minimum value, where that maximum and minimum value will always fall at either the endpoints of that interval, as we see here in the couple of these graphs here, or at the critical points, the other values where we would expect the slope of the tangent line to be equal to 0 or to be undefined and not exist. And that case wouldn't very seldomly happen if we're going to be continuous. Yeah. Should be careful saying that, though. I should really be careful saying that. But if we exist on a closed interval, we'll always have either both a maximum and a minimum absolute value. All right, absolute max or extreme value. Absolute extreme value. And there is a procedure for finding those extreme values on some closed interval. There's actually a procedure that we can follow because of their known existence and where they are located. So we do have this process here of finding absolute extreme values of a function on a closed interval. It says consider the function y equals f of x on the closed interval from a to b in the domain of f, where f is continuous on this closed interval. The first thing you're going to do is find the critical points of f. And more specifically, find the critical points of f that are in that interval from a to b. What you're then going to do with those critical points and with the endpoints from the values a and b is you're going to evaluate your function f at each of those critical points and at those endpoints of a and b. Since we know those critical points or those endpoints will be where we expect absolute maximum or minimum values, the largest value that we find for f at either those critical points or those endpoints will be our absolute maximum. And the smallest value we find for f at those critical points or at those endpoints will be the absolute minimum value of our function. So basically, if we know our function exists on a closed interval, find the critical points on that interval and analyze the output of the function at the critical points and at your endpoints. If the endpoints are larger or smaller, then those will be your absolute max or mins. But if a critical point produces a larger or smaller maximum value than when compared to the output of the function at the endpoints, then that critical point, or the other critical points, then that critical point will be the location of that absolute extreme value. Because they have to be at those two locations, then just look at the function at those two locations and say which is the largest and which is the smallest. You're the absolute extreme values. Consider the absolute extremes on this polynomial. 2/3 x cubed minus 3/2 x squared minus 5x over values of x in the interval from 0 to 3. If we find the critical points of this interval, we're going to find the first derivative of our function here and set it equal to 0. And we'll notice it equals 0 at -1 and 5/2. Those are the only critical points. -1 and 5/2. And more specifically, 5/2 is the only critical point between 0 and 3. -1 is smaller than 0, so it's not even in that interval. So the only one we have to test against is 5/2. All right. So I'm going to test 5/2 by plugging it into my function and seeing what the output is. and comparing that to the output of my function at 0 and 3. Now, I do that in a table here. And you'll notice when I plug 0 into my function, 0 is going to produce 0. Whereas if I substitute 5/2 into my function, that is going to produce -11 and 11/24. Whereas when I substitute in the value of 3, the output of the function is -10 and 1/2. From my selection here, I can see 0 is actually the largest value of f on this interval, and -11 and 11/24 is the smallest value on this closed interval. So these must be our absolute extreme values. The absolute max occurs at 0 and is 0. The absolute min occurs at 5/2 and is -11 and 11/24. We can see this in the graph. If we graph this function over this closed interval, we will see these extreme values. Over this closed interval, this is what our function would look like, just this little portion of a curve. Where certainly you can see here at x equal to 0 is where we have the absolute maximum value on that closed interval. It is at the value of 0. Whereas the absolute minimum occurs at this location, which is at the negative, or at the value of 5/2, 2.5, which is at -11 and 11/24, which is at this location seen here. That's our absolute minimum value. And that can be seen in the graph for this closed interval. All right? If our function is bounded on the left and the right, you're going to have both a maximum and a minimum absolutely. How do you find those absolute maximum and minimum values? Well, you look for the critical points that lie between your boundaries of A and B. And you calculate the outputs at A and B and compare that to the output of the function at your critical points. That's what we're doing here in this table. And whatever is the largest output is your absolute maximum, which 0 was, which is kind of funny to say that that's the largest value, but it is for the function. And the smallest output for the function is -11 and 11/24. So it's our absolute minimum value. This is absolute extreme values, folks. On an open interval, you're going to have to analyze the range. And all absolute extreme values do describe is the range of our function. It's either the range over the entire domain, or it's a range over a portion of the domain. But all the absolute extreme values describe would be the finite values seen within those range descriptions. The absolute minimum on the low end and the absolute maximum on the high end, if those values are finite. When we're on a closed interval, they're guaranteed to exist, and we have this process of finding them, which we just looked at in this final example. Again, it's all an analysis of the range. You have to think about what is the range of my function on either this open interval or on this closed interval where I'm examining the output of my function. It's going to happen at the endpoints on a closed interval or at the critical point. And if you're not on a closed interval, well, then you have to do a little bit further analysis. This is where taking it all, putting it all together, and perhaps maybe graphing our function over that open interval or semi-open interval is going to help you start to determine those values exactly. But if it's on a closed interval, you know you have an exact procedure for finding these. Take note. All right. We're going to come back and talk local extreme values. We're going to have to introduce what's called the first and second derivative test. This is probably going to be a little longer set of notes. What I probably should do is break it up. Maybe I will break it up. I'll break it up into the first derivative test and the second derivative test. And that'll make the videos a little shorter. So let's do that. Let's come back. We're going to come back and look at, in the next set of videos, finding local extreme values. One way is using what's called the first derivative test. The other way is going to be by using what's called the second derivative test. And we will set those up in our next video, folks. But with that said, I will end this video here, and I'll see you in those next ones.